Okay, hello ladies and gentlemen, welcome to my today's talk about influence of manufacturing condition on the surface quality of stainless steels in sensitive applications. My name is Arnold Feldnagel. I'm a professor at the THWS, the Technical University of Applied Science in Würzburg-Schweinfurt, and I'm very pleased to give you today's talk about stainless steel surfaces and how the manufacturing process and the machining process is influencing the properties of these special materials. The project I'm presenting today was carried out in collaboration with our partner BOLZ INTEC GmbH. BOLZ INTEC is a specialist in the production of high-quality stainless steel vessels, especially for sensitive applications like food industry, pharmaceutical industry, and the chemical industry as well. In order to limit this very wide range of topic, I have focused in our project on vessels and containers with a small amount of volume, up to 200 liters, and especially for applications like tempering, searing, mixing, or even just for storaging sensitive goods. As I said, even if the volume of these vessels is limited in this topic, in this area, the market value of the containing goods quickly reach a volume of several million US dollars. So the goal of the project is to reduce the manufacturing costs at one side and also reduce cleaning costs or reduce the risk by contamination these very expensive goods inside the vessels. The manufacturing of these components is normally carried out by using stainless steels, high grades of stainless steels, for example, like 4A grades like the 316L, for example, but for some applications there are only lower grades like 304 used. The standard regulations is given by different ISO standards. There are some regulations according to surface quality, according to the look of these projects, and to reach these high requirements, and especially to meet the hygienic requirements, that there are no surface defects. The surface roughness you have to reach is less than 0.8 micrometers. And the surface must be easy to clean and homogeneous. But unfortunately, there are not more specific requirements given by ISO standards, so that's the reason why there are mostly some additional customer requirements. Well, talking about influencing factors. Factors, they are influencing the quality of the surface, and they are also influencing the quality of the good inside our vessels. Well, first, talking about the production itself, depending on the production process, the surface roughness is influenced, the surface topography is influenced, and of course, the uniformity of the surface itself can be influenced. The chemical composition of the surface can be influenced as well, maybe by using some special chemical treatments to increase the stability of the passive layer. And on the other hand, of course, we have some influencing factors from the product inside our vessel, for example, by the molecular structure or by the process parameters like temperature, humidity, flow velocity, and so on. So these factors all together are influencing the interaction between our good and our stainless steel surface. And if we're talking about surface, we also have to talk about surface roughness. I guess it's well known that we have different standards to characterize surface roughness, for example, like the ISO standard 4286 to characterize surface roughness by the Ra value. And I guess it's also very known in common, or it's known by many people, that surface roughness like Ra, for example, 0.8 micrometers can lead to very, very different surface topographies. Like shown here, you can have a very nice homogeneous structure, but you can also have a structure like this or like this. So even if we have a standard surface roughness smaller than 0.8 micrometers, we must be aware that you can have complete different surface conditions. And if we take a closer look on a surface, maybe on a ground surface, like shown here, industrial ground of a 301 stainless steel, you can see we have different surface properties, we have different chips left on the surface, depending on the kind of surface preparations. The left side was carried out by an alumina oxide grinding abrasive material, the right side was done by silicon carbide. And even with the same grinding parameters, you can see you have different kind of surfaces. And if you, for example, add some additional machining like brushing, for example, you can also see that in a closer look you have microstructures left on the surface. You can see some grain boundaries by the pre-treatment process, by the chemical pre-treatment process, which was carried out before the brushing. And these grain boundaries are very risky, for example, if you are in contact with aggressive or corrosive goods, or even if there are some microorganisms in your goods, or that they can stay there in these microstructures and leads to a contamination of your good. And of course, grinding itself leads to metal chips. They can be left on the surface, and also some microstructures like shown here, where you have areas where also some scratches can be, some deep scratches can be in the surface, and these microstructures can reduce the corrosion resistance at one hand and can lead to a higher contamination, higher rate of contamination of your good at the other hand. Talking about machining, we always have to take into account that by machining a surface of a steel or a material, especially stainless steels, you have an interaction between a tool and your material. The material itself can be influenced by the mechanical machining, and the depth of this influencing factor is influenced by the way you do the machining. Like shown in 1947 by Wolf, we have this so-called Bailey layer, and this called Bailey layer can be influenced by different ways of machining. If we do a smooth machining, like honing, on a honed structure, we have only a very thin layer, a very thin Bailey layer at the top. If you do a harsh machining, a harsh grinding, we're influencing this Bailey layer down to several micrometers, maybe 20, 30, 40 micrometers into depth. And if we do electrochemical polishing afterwards, we are able to remove this Bailey layer, we are able to remove this deformed area, and so we have a very nice homogeneous metallic structure left without any deformation on the surface. But you have to take into account that the depth you can do electropolishing is limited. That means if you do a very harsh machining, a very harsh grinding on your surface, which is going to affect the depth of your material down to 40, 50, 60 micrometers, you may have some problems to remove everything of this Bailey layer by the machining, by the electropolishing process itself. And what's the goal of electropolishing? Of course, the goal of electropolishing is to get a homogeneous structure, a homogeneous surface, And of course, it's also a goal to reduce, to increase the corrosion resistance, so to reduce the effect of local defects on the surface. Talking about corrosion resistance, we are always talking about corrosion resistance, and for stainless steel mostly about critical pitting temperature or critical pitting potential. In this case, we carried out some tests by the critical pitting potential, like according to the ASTM standard. And by local defects, you have a decrease of the critical pitting potential, means your surface is weaker against corrosion. But before we telling you something about the corrosion resistance, I will illustrate the change of mechanical properties, maybe by processes like cold rolling. Like you can see here, we have a stainless steel 304, and by cold rolling you have an increase of the tensile strength of the material by a decrease of the elongation at fracture. So if you do cold rolling, you increase the tensile strength, you're decreasing the elongation at fracture, and this is something what was carried out in combination with different kinds of surface preparations. First, we did some cold rolling, afterwards we did some surface preparations, and by standard metallographic polishing in the laboratory, you can see the corrosion resistance shown by the critical pitting potential is decreasing by an increase of cold rolling at the material. Means leads to a lower corrosion resistance. If you do some electropolishing on the same kind of surfaces, you also have the decrease of corrosion resistance with an increase of cold rolling. And if we take a look at a metallographic ground surface, so grinding by hand, you can see that grinding by hand leads in this case to a small increase of the corrosion resistance by an increase of cold deformation, which means that you have different effects. Here they are leading to a change in the corrosion resistance, but if you do grinding by hand, you are able to increase the corrosion resistance slightly, even if you have cold deformation. So, coming back to baby layer, it means we always have an interaction between our manufacturing process and the surface, and how the manufacturing process, how the machining process is going to influence our surface conditions. And this was the starting point for the project we carried out in cooperation with our partners, where the idea was we have to improve our manufacturing process, our machining process of these stainless steel vessels, to increase the surface properties and to increase cleanability, to get better surface conditions and to reduce risk of contamination of these very expensive goods. If you're doing the manufacturing of a vessel like this, of course you have some rolling, so you will have some grinding afterwards, and of course you have welding as well, so you have to remove maybe these areas around the weldings, and this is normally done by some manual manufacturing processes. So you have pre-treated surfaces, you're doing the welding, you're doing the cutting, the grinding, then you do mostly a manual hand-guided grinding, for example by an angle grinder, and afterwards you do electropolishing on these vessels. And the goal of our project was we want to replace especially the hand-guided machining, because this is very risky. If the people that are carrying out this manufacturing process are not well trained, it's very risky that they are going to make some scratch, they're going to destroy the surfaces and even make a very deep deformation inside the material, which leads to a very huge problem, especially with the baby layer. And so the goal was to remove this hand-guided machine process by an automated process, especially by a slide grinding process. And therefore we did a lot of different tests, and we realized that we have to do to get a very good quality of our surface, we have to do the grinding process by ceramic bounded current, aluminum oxide, and of course it got a name as the process got a name. It was called optimized grinding finish. So this is the name given by BOLZ INTEC. Okay, and how does a surface look like? Well, starting with a standard surface of stainless steel, you get by your steel supplier. If you do a normal grinding process, a ground surface like shown here, you have this linear structure by the grinding, and if you do this optimized grinding finish, you see that you have a homogeneous structure, no linear structures left on the surface, and if you do electropolishing afterwards, you can see even after electropolishing, you can see linear structures on the surface left by a standard ground surface. But if you did OGF first and then doing the electropolishing afterwards, you can see you have a very homogeneous structures with no visible, a very homogeneous surface with no visible structures left. And even if we take a look at the surface roughness, we reach after different steps. Gray areas here are going to show the surface roughness by grinding. So starting with a very rough grinding process of a grain size of 40 or 80 leads to very high Ra values. But increasing the different steps, we can reach maybe 0.4 to 0.5 micrometers, and afterwards, if you do the electropolishing, you reach maybe 0.2 micrometers surface roughness. If you do the OGF process, you can reach the roughness like grinding and electropolishing right now after the OGF process, so you reach a surface roughness at about 0.3 micrometers or maybe 0.2 micrometers. And if you do electropolishing afterwards, you're also still able to reduce the surface roughness again. So you can reach 0.12 micrometers of surface roughness. That's about the roughness. And talking about the cleanability of the surface, you can see cleanability according to ISO 16232 in different machining states. If you do a conventional grinding or brushing and doing electropolishing afterwards. Here you can see the number of particulars depending on the size of the particulars. So the standard way you're doing this test is you have a defined surface, putting this special dust on the surface and then cleaning the surface, and after cleaning the surface you're going to count what's left on the surface. So this is the number of particles depending on the size of the particles. And you can see by electropolishing, so the slight blue line here, according to the blue line here, is the machined and electropolished surface. You are able to reduce the number of particles left on the surface by electropolishing. This is for the conventional grinding. If you do the OGF process, you can see only after OGF the number of particles left on the surface is increased compared to only grinding. But if you do electropolishing on this surface afterwards, you can see in very strong degrees on the particles left on the surface, and especially if you compare the numbers of the particles left on the surface after OGF compared to the particles after conventional grinding and electropolishing, you can see that there is an increase of cleanability by the OGF process in combination with electropolishing. So, to come to a conclusion, it's possible that we have a reduction of the mechanical influence in depth by the OGF process. So this leads to a more homogeneous surface after the grinding. We have less imperfections left on the surface, and we have an improvement of the surface properties, especially regarding to the cleanability behaviors after electropolishing. This whole post-processing, like electropolishing, is always increasing the surface properties. And of course, electropolishing is able to remove imperfections, but if you have imperfections on the surface by the machining process, you are unable to remove every kind of imperfection, and you are unable to remove every kind of dislocations inside the surface only by electropolishing. So it is very important that you have to take. It's very important that you take into account that you have this belly layer, and every kind of machining process you're going to do is influencing this surface and is influencing the belly layer itself. If you reduce the depth, this belly layer is influenced by your machining. So if you are not going to do a very harsh machining, if you do a very slight machining and reach a good surface condition by the slight machining, you have better surface conditions, you reach a better cleanability, and especially post-treatments like electropolishing leads to a better quality of your surface. Thank you very much. Have a nice day.